Good day, everyone. My name is Xavier Liong with the entry number 86079, and today I am presenting my final year project 1, titled Encrypted Chat System with Self-Destruct Feature. I am supervised by T.S. Haji Ahmad Hadinanda bin Fauzi, and I am honored to present my work to my examiner, Associate Professor Dr. Chai Susi. This project addresses a critical gap in law enforcement technology: the need for a communication channel that is completely sovereign, secure, and leaves no digital thread behind. Here is the agenda for my presentation. I will begin by setting the context in the introduction and defining the specific problem statement. I will then outline the objective and scope of the project. We will look at the literature review where I analyze the gaps in the existing apps like WhatsApp, Signal, and Telegram. A significant portion of this presentation will focus on the methodology, specifically the requirement I gathered from the head of security police Bantuan UNIMAS. Then I will deep dive into the technical system architecture, cryptography implementation, and database design. Finally, I will share the implementation status and my testing strategy before concluding. Let's go to the chapter 1 introduction. Let's start with the context. In the modern digital landscape, law enforcement agencies like Police Bantuan UNIMAS rely heavily on digital communication for operational efficiency. However, they currently face a dilemma. While traditional apps like WhatsApp are convenient, they introduce significant risks regarding data sovereignty, meaning we don't know exactly where the data is stored, and the persistent storage, where messages live on servers indefinitely. My proposed solution, Sentinel, is a secure web-based platform tailored specifically for their needs. Its core concept is zero-knowledge architecture combined with a self-destruct mechanism, ensuring that sensitive intelligence is never permanently stored. I have identified four specific problems with the current solution used in the field. First, permanent storage. Even if an official deletes a message on their phone, threads often remain in the provider's server backup or database log. Second, data privacy. Many platforms retain plaintext data on the server. If the service provider is compromised, sensitive police intelligence is exposed. Next, insider threat. This is the critical operational risk. If a device is lost or an account is compromised, the entire chat history can be recovered by unauthorized personnel. Finally, lack of control. Users fundamentally lack of ability to verify if a message has been truly erased from the recipient's device. You just have to trust the other person delete it. Sentinel addresses this problem with four security pillars. First, end-to-end encryption. I am implementing AES 256 via the Web Crypto API. This ensures that plaintext never leave the client device. Second, data sovereignty. Unlike commercial apps hosted in the US or Europe, Sentinel is hosted locally on XAMPP, keeping all data physically within the UNIMAS intranet. Next, self-destruct. I have designed a cryptography erasure mechanism that triggers automatically upon reading or timer expiry. Finally, compliancy. We use a hybrid policy where the message content is destroyed, but encrypted audit logs are retained for 30 days to ensure accountability. The specific objectives of this project are: first, to develop a secure web-based chat system that enables real-time communication; second, to design a robust self-destruct feature that allows officials to set destruction rules either after read or after a set duration. Third is to evaluate the system's performance, specifically focusing on encryption efficiency and the accuracy of the deletion mechanism. To ensure the project is feasible and high quality, I have clearly defined the scope. Inclusions: a one-to-one chat interface, comprehensive user management like registration, login, admin dashboard, the core end-to-end encryption module using client-side key generations. Exclusion: I will not be developing group chat. There will be no native mobile apps like iOS or Android. It is a web-based app. No voice or video call. This allows me to focus purely on the security of text and file transmission. Let's go to chapter 2, literature review. In my literature review, I analyzed the three market leaders. First is WhatsApp. It uses the secure signal protocol, which is good. However, it relies on phone numbers, making identity management difficult for an organization. Furthermore, cloud backups like iCloud or Google Drive are often unencrypted, leaving a battle for data leaks. Next is Signal. This is considered the gold standard for privacy, but like WhatsApp, it ties identity to a SIM card. This is an operational security risk for officials who may not want to use personal numbers for official duty. Next is Telegram. It is popular but has a critical flaw. It does not use end-to-end encryption by default. You have to manually start a secret chat. This creates a high risk of human error where officials may accidentally share intelligence over an insecure channel. This table summarizes the gaps Sentinel fills. Identity: commercial apps using phone number, Sentinel using internal username, separating personal identity from professional duty. Hosting: they use foreign cloud, Sentinel use a local server, ensuring data stay in UNIMAS only. Default security: Telegram is opt-in, Sentinel is secure by design. Encryption is always active and cannot be disabled by the user. To build this system, I reviewed the underlying cryptography technologies. TLS, which is Transport Layer Security. This secures the connection HTTPS, but protection ends at the server. It is insufficient for a zero-knowledge requirement. AES-256. I chose AES over RSA for message encryption because it is the NIST industry standard and offers much higher efficiency for mobile device. Defeat Hellman Key Exchange (DHKE). This is essential. It solves the key distribution problem by allowing two parties to generate a shared secret over the web without ever sending the key itself. Web Crypto API. Finally, I utilize the native browser API. This is significantly faster and more secure than using external JavaScript library, which can be vulnerable to side channel attacks. Let's go to chapter 3, methodology. I am following the interactive system development life cycle. Why interactive? Because security requires precision. This model allows me to develop and test the cryptography components like the AES logic and the key exchange in isolation before integrating them into the full user interface. This approach minimizes the risk of catastrophic security failures during the final deployment. For the phases, I start from analysis, followed up by design. Next is prototype cycle and testing, and the final is the deployment. To ensure the system is practical, I conducted a structured interview with Mr. Rajan Tengavelu, the head of security at Police Bantuan UNIMAS. He provided two critical insights that shaped my project. First is about risk. His primary concern is the human element. Insider leaks are a bigger threat than external hackers. Next is about hosting. He confirmed that hosting on external cloud server is unsafe for their operational, so he suggests using local hosting is a mandatory requirement. Mr. Rajan's feedback directly influenced my design strategy. First is about zero threats versus accountability. He noted a conflict. While they want privacy, they need accountability for internal investigations. So my solution is using a hybrid retention policy. The message content is deleted immediately, but encrypted compliance log are kept for 30 days via automatic cloud jobs. This is about suspect photo. He noted that photos of suspects need to be printed and filed, so immediate deletion would hinder operations. So my solution is I will configure the retention timer to allow 3 to 5 days for specific operational data. Based on this, the functional requirements are: first is user management. We use bcrypt hashing for password and distinct organization IDs. Next is messaging, real-time transmission where only ciphertext is sent. And the last one is self-destruct. Two trigger, which first is read receipt trigger for immediate deletion, and the second is time-based trigger for that 3 to 5 days window. For the non-functional requirement, the system adheres to strict standards. First is zero knowledge. Server admins must never have the key to decrypt message. Next is performance. Encryption latency must be under 100 milliseconds to ensure that the chat feels instant. The last one is standard. We strictly adhere to NIST FYP 197 standards for AES 256. We also addressed serious ethical concerns regarding data destruction. First is accountability versus privacy. The risk is that the official could use self-destruct to hide misconduct. The solution is our mandatory metadata logging. While the content is gone, the audit track of who spoke to whom remains visible to the chain of command. Next is suspect rights. Currently, officials might keep suspect photos on personal phone indefinitely. Sentinel enforce data minimization by auto-deleting this image, ethically protecting the privacy rights of the public. Now, let's look at the system architecture. I designed a three-tier architecture. First is client tier. This is where the logic lives. The HTML or Bootstrap UI and the Web Crypto API handle all applications here. Next is application tier. The Apache or PHP server acts merely as a relay. It processes requests but never see the plaintext. And the last one is data tier. The MySQL database store only the encrypted ciphertext. This block diagram visualizes that separation. Please look at the client here. You can see the crypto module is entirely contained here. The data flow shows that only JSON data containing ciphertext is sent to the PHP engine. This confirms that key never leave the user's device, ensuring data sovereignty. For the cryptography itself, I am using AES GCM Galois counter block. I chose GCM because it provides authenticated encryption. It verifies data integrity to ensure the message wasn't tampered with during transit. The key strength is 256 bits, which offers a complexity of 2 to the power of 256, effectively impossible to brute force. All of this run on the Web Crypto API for native browser performance. But how do we share that AES key securely? If we send the key over the network, it could be intercepted. To solve this, I use the Diffie-Hellman Key Exchange (DHKE). This protocol allows two parties to exchange public parameters and mathematically derive the same shared secret independently. without ever transmitting the private key itself. This sequence diagram details the exact timing. Phase 1 at the top. You, you can see the key exchange. The sender and the receiver exchange public key via the server to derive the AES key. Phase 2 in the middle. The sender types hello. The client encrypted it to SY9 and only SY9 the ciphertext is sent to the PHP server and stored in MySQL. The receiver then fetch SY9 and decrypt it locally. Phase 3 at the bottom. Once the read receipt is triggered, the client sends a delete request to the database, removing the message ID permanently. The logic for that deletion is shown in this flowchart. We have a dual path. Path A, if the mode is immediate after read, the message is deleted the moment the user views it. Path B, if the mode is timer, a server-side cron job check for the expired timestamp and perform a void delete. Both paths lead to the same outcome, which is removal from UI in the database. Our database design enforces this security. Look at the message table. It has columns for ciphertext content, IV vector, and expiry time. Crucially, there is no column for plaintext. The users table stores the public key needed for the exchange. The system logs table tracks aiming action for compliance, but holds no message data. Here is the user interface design. The login is minimalist and strictly for authorized personnel. The chat interface clearly indicates the security status. You can see the end-to-end encryption active batch and the red timer countdown, ensuring the official is always aware of the data lifespan. For the development, I am using Zen to simulate the local intranet environment. The Bootstrap 5 is for a mobile responsive UI, and the Visual Studio Code is my primary IDE. I have planned the implementation in four interactive cycles. Cycle 1, establish the core infrastructure and secure authentication. Cycle 2, build the real-time communication interface. Cycle 3, this is the most critical phase, which is integrating the cryptography module, end-to-end encryption, and the key exchange. Cycle 4, finally implementing the self-destruct mechanism and automation scripts. My testing strategy covers four areas. First is functional, verifying that messages are actually deleted when the timer hits zero. Second one is durability. I will use OWASP ZEP to scan for SQL injection as SSS attacks. Third one is security. I will manually inspect the database to prove that only ciphertext is stored. And the last one is performance. I will measure the encryption latency to ensure it stays under 100 milliseconds. In conclusion, Sentinel provides a sovereign, locally hosted, end-to-end encrypted solution tailored for police Pandora UNIMAS. This is impact. It mitigates insider threat and enforces strict data lifecycle management, solving the privacy issue inherent in commercial apps like WhatsApp. And the last one is status. The methodology is defined, the architecture is fully designed, and the project is ready for the implementation. That concludes my presentation on my FYP1. Thank you for your time and for your listening.